Hi, today I'm going to talk about the solutions for Atcoder Beginner Contest 400 problems A to F. And for problem A, we have A rows and B columns, and we want to arrange 400 people in these A rows and B columns. And so we're given the integer A, and we need to print out the value of B to arrange these people in A rows and B columns. And we need to find the integer B and determine whether it is possible. If not, we can just output -1. And so for this problem, we can just directly check if 400 is divisible by A. And let's look at the code for specific details. So here we just input the value A, and then we check if 400 modulo A is equal to 0. So if 400 is not divisible by A, then we can conclude that no possible value for B exists. So we just output -1, and if else, we output 400 divided by A. Next, we look at problem B. For problem B, we have two positive integers n and m, and we need to output the sum of this. And this will be a geometric series, and we need to output its sum. And so if the sum is greater than 10 to the power of 9, we need to print out INF, and otherwise we need to output the value of x. And so for this problem, since n and m are since m is small, we can just directly calculate the values for i from 0 to m. So let's look at the code. So we can keep track of a variable to keep track of the product and also the current sum, and we can just loop through I from 1 to m, and then for each one multiply the current product by n, and then add the product to the current sum. And we can continuously check in each time of the loop whether the current sum is already greater than 10 to the power of 9. So if it is, we can output INF, and otherwise at the end, the current total sum will be outputted. Next, we'll look at problem C. For problem C, we have a positive integer s, and it's called a good integer if it can be factored into 2 to the power of a times b squared. And so, for example, 400 is a good integer because 400 is equal to 2 to the power 2 times 10 squared. And so, when we're given a positive integer n, we need to find the number of good integers between 1 and n. What we can do is we can create a list of exponents of 2 within the range of 10 to the power of 18, since n can be as large as 10 to the power of 18. And since the number has to be factored into 2 to the power of something times another number squared, we can loop through the list of powers of 2 and perform binary search on the maximum possible value of b. And in this case, b, as we just mentioned, is the value that has to be squared. So, and we need to notice that in this case, it's important to only count all the values of b, because if b is even, then it can be factored into 2 to the power of 2 times k to the power of 2. Here. And So this means that it will be overcounted when we when we loop through the power of 2, another power of 2, and then when b is a value of k. So in this case, since 2 to the power of 2 can be factored out, this will be overcounted. So we only need to count odd values of b instead of even values. And let's look at the code for more specifics. So I first generated a list of all the exponents of 2 in a vector of long longs, and then I looped through all the powers of 2 as I just mentioned. And for each one, I binary search on the maximum possible value of b. And since this part is the binary search, and the minimum possible value of b is 1, and the maximum is square root of n divided by the current power of 2. And since we only need to find the odd values for the increment of answer, we can divide the value by 2. And I do first plus 1 divided by 2 because, for example, because I want the numbers to round up instead of round down. So, for example, when first is a value of 3, then the odd values would be 1 and 3. So I want 1 and 3 to both be counted, so I would add 1. So it will round up instead of down. And afterwards, we can just output the answer. For problem D, we have a town, and then there's H rows and W columns, and each cell is either a road or a wall. And we start at cell AB, and we want to end at cell CD. And each move, if a adjacent cell is a road, then we can just move there without any front kicks, and otherwise we need to perform a front kick, which is in the current direction that we're facing, and it would destruct the walls that are at most 2 steps away in our current direction. So our goal is to get from the start to the end in the minimum number of kicks needed. So yeah, let's look at this problem in more detail. So for this problem, we can see that we can perform BFS, since this is a typical problem of a grid. And for this one, we notice that all adjacent cells that are rows have a cost of 0 to move over there. And for all cells that are 1 step or 2 steps away in the direction, and then if there are walls, they will cost a value of 1, since a front kick is necessary. And so we can store the minimum number of kicks needed to reach grid ij in a 2D array Fij, and then we can perform a BFS starting from cell AB as given in the problem. And so we can use a deck to store the BFS values, since this way we can push the cells that cost 0 to the front and cells that cost 1 to the back of the queue. So this is because we want to minimize the number of kicks, so we want to process the cells that cost less first to reduce the time complexity, so we don't have to process it many times if we do it like not in order from these two greatest. And I guess this can also be done with like a priority queue, but I think using a deck is fine. And so this is important since if we don't do it in this order, this would the algorithm will have to process it many times and it will exceed the time limit. And let's look at the code. And so for this part, we just first all the inputs, and then this was the F is the array that I mentioned that we can use to store the minimum number of front kicks needed to get from the start cell to the end cell. So we can first fill in all the values of F with a large value, and then we can set the starting location of F to 0. And afterwards, this part is the BFS. And so we start with our starting location, and then for each step, we can loop through the 4 directions adjacent cells, and then for each cell, and this part is when the adjacent cell is another road, and so we can just directly go over there without a cost. So we would push this to the front of the queue, and otherwise this is one step away, but then there's a road on that cell, so one front kick is necessary. So since a cost of 1 is necessary, we would push this at the end of the queue. And this part is processing the cells that are 2 steps away. And so for this part, for cells that are 2 steps away, this part is like simulating a front kick. So it would require a cost of 1, and we would push it back at the end of the queue. And so when we're looping through adjacent cells, we can create an array like this and then loop through the 4 directions. And for each, we can update the coordinates of these cells using the array we created. And so at the end, after the BFS, the FCD will be the minimum number of front kicks needed to arrive at the end location. For problem E, we have a positive integer n, and it's called a 400 number if it satisfies the conditions that it has only 2 distinct prime factors, and for each prime factor p, it divides n an even number of times. And so there are several 400 numbers, and we need to process these queries that for each query we want to, when we're given a integer a, we want to find the largest 400 number that doesn't exceed a. And so we notice that there are several queries, so we can't reprocess all the numbers for each query. So in this case, we can first compile a list of all the 400 numbers, and then for each query we do binary search, since we can sort all the valid numbers in order, and then we can do binary search and find the maximum value that doesn't exceed a. And yeah. So, yeah, as mentioned, we can just first process all the valid numbers up to 10 to the 12 because the problem mentioned that A would be up to 10 to the 12. And then we can do binary search for each query as mentioned. And so we can first compute all the primes up to 10 to the power of 6. And so it is 10 to the power of 6 because A can be up to 10 to the power of 12, and the prime has to divide n a even number of times, so it will at least be a power of 2. So we can just compute primes up to 10 to the power of 6 and no need to do any larger number. So we can process all the primes in, I think, O n log n time, if I'm not wrong. And so we can do this by looping through all the values from 2 up to 10 to the power of 6, and then for each value we mark all of the multiples of that value as not prime, and then afterwards we can just add all the values that haven't been marked as not primes into an array, which can be our primes. And then we can look at this afterwards when we look at the code. And so afterwards, when we have a list of primes, we can loop through the list to generate some valid values that adhere according to the conditions satisfied in the problem. So we can look at specifically how to do this in the code, but then one thing to remember is that when the value exceeds 10 to the power of 12, we can break whenever the value exceeds 10 to the power of 12 to ensure that it doesn't exceed the time limit. So here, this part is the part about the primes that I mentioned. So we can first create a array that is marked as true. And then later we can loop through the values from 2 to 10 to the power of 6, and then for each, if this number is already marked as a non-prime, we continue because all of its multiples would have been marked already. And afterwards, if it's not, so if it's still marked as true, then this means that it's a prime, since none of the smaller values were divisors of it. So afterwards, we loop through all the multiples of I, and then we mark each as false, so they're not primes. And then now we have a list of primes stored in this vector P. And afterwards, since we want to create numbers that are even divisors of these numbers, so we can loop through the array of primes that we created, and for each we can update this is the first prime, since it needs to have only 2 unique prime factors. So this is the first prime factor, which I named PA, and then PB is the second prime factor. And so we can start with PA and then first start with a power of 2, since a power of 2 is the minimum. And for this, we can check like again, I mentioned that we can break whenever it's needed. So if the next prime also a minimum of power of 2, so this is the smallest combination possible with the current prime number. So with this prime to the power of 2 and the next prime to the power of 2. So if their multiple is already greater than 10 to the power of 12, we just break. And then afterwards, for this loop, this big while loop is incrementing like the PA. So each time we're multiplying 2 times like PI squared. So in the inner loop, I'm looping through the second prime number. So I only start from I plus 1 since there's no need to start from 0 since it will already be accounted for. And for this, I do the same thing and then check if the value is already greater than 10 to the power of 12. And otherwise, if PA times PB, so again, PA is the first prime and PB is the second prime. And so if this is less than or equal to 10 to the power of 12, we can push it back into a vector called num, and then this is the vector where I store all the valid 400 numbers into the vector. And yeah, and then afterwards, after this loop, we finished calculating all the valid values for all the valid numbers, and then we can ensure that there are no repeated elements by sorting them, and then we need to sort them for later binary search. And afterwards, we can erase all the repeated values. So now we have a list of all the valid numbers in order, and then we can process the queries by performing upper bound, by using upper bound and then -1, since this will give us the value that is less than or equal to A, and then we can output that value. Next, we have problem F, and then for this problem, we have a circular cake that's cut into n equal sizes, and initially, every piece is colored 0. And so we can perform an operation which is to choose a range on the circular cake and then modify the range into a specific color. So let's look at one example, and then so for this, initially all the slices are colored 0, and then afterwards we can color a specific range, in this case it's this number, into another color. And then when we color it into when we change the color, the cost of this operation is the number of slices that we color plus the XC, and the XC is given, and C is the new color that we're changing into. So we're given X, which is the price for each color, and then C is the desired colors that we want the cake to look like in the end. So in the end, we want each slice to match the colors given in the array C. So in this part, we can update each operation is a range. So for the second operation, it updates these 3 numbers into color 2. So yeah, and then this would have a price of 5 since we're modifying it into the color 2, and then x2 is 2, and then we updated 3 slices, so this adds 3 to the cost as mentioned previously here. So for this problem, the n is only 400, so this is likely a n to the power of 3 solution. So we can define we can use dynamic programming, and for this we can define FLR as the minimum cost to change a range LR, like to change this range into the desired colors, which are the colors in the array C. And so since this problem is a problem on a cycle, but then it's hard to deal with the values in the cycle since it's hard to deal with the indexes when the values are in a cycle. So we can break the cycle by duplicating the array. So we can just duplicate the array, and the range of f will become 1 to 2n since we duplicated it. And so if we look at the transitions into different states, for FLR, there are 2 possibilities. One is the last value, like the last cake slice R, is one distinct operation on its own, and in this case FLR is equal to FLR minus 1 plus the cost to change this cell on its own. So the cost to change this cell on its own is XCR since we want to modify it into color CR, and then since this operation has a length of 1, we add 1. And so there's another possibility, which is that the operation on R combines with another previous operation. So we can loop through K from in the range L to, this is L, and then L to R minus 1. And then if CK, which is the desired value of cell K, is equal to the desired value of cell R, we can check if we want to extend the operation on K to the range of R. So this means that for L to R, if this is K, this part is K, and then R is here, right? And then, so this means that for the operation on K, we can extend it so that this also covers the range up until R. And so the cost of this would be, since if we are just extending the operation, we only need to add the number of cells that we extended by. So this is the number of cells that we extend the operation by is R minus K. And then, so this would be the cost to change the first section into the desired colors, which is FLK, and the cost to change the middle section into the desired colors, since after we perform this operation, we need to change the middle section back into the desired color. So this is FK plus 1 to R minus 1. And so we need to find the minimum value over all valid K and update FLR accordingly. So if this is unclear, we can look at the code. So initially we input all the values, and then this part is duplicating the array since we want to duplicate the array to break the cycle. And then for initializing the values for fii, since this is just one cell I, the only operation is to update it directly, so the cost would be xci plus 1. And then this part is updating flr, and we need to start from lengths that are shorter, since greater lengths values would depend on the ones with shorter lengths. So we start from shorter lengths, and then this is L and R. We can loop through L, and since we already have the length, we can use L and length to determine R. And then if R is greater than 2 times n, we need to break out since this exceeds the limit. And this part is what I mentioned when the last cell R is only one distinct operation on its own. So it is the cost to update the cells from the slices, the cake slices from L to R-1, which is stored in FL R-1, plus the cost to update the last cell, which is what we updated earlier, and this is FRR. Afterwards, this part is what I mentioned about extending one operation previously. So we loop through all possible values of k in the range L to R-1, and then if the desired colors are equal, we can consider extending the operation to the end. So this part is the front, and then this is the cost of extending the operation, since we would paint R minus k more cells, so it would cost R minus k more. And this part is the middle, since after we extend the operation, we also need to update the middle part, k plus 1 to R minus 1, back into our desired values. And this is the cost for doing that. And we can find the minimum of all possible ways we can update this range, and then store it in FLR. And afterwards, I think I forgot to mention previously, is how to calculate the answer. So for the answer, we can loop through starting points from 1 to n, and then we can find the minimum to paint this range, and then the range would have a length of n, and this will have all the cakes since there are n cakes in total. And then so since our range is inclusive, it would be from I to I plus n minus 1, and we find the minimum of all of these values. And afterwards, we simply output the answer. And thank you for listening.